Another reaction is the reaction of alkene with halogens, and the halogens can be either bromine or chlorine. We don't use iodine and we don't use fluorine. Fluorine is very reactive, and iodine is unreactive. So we don't use them. We just use bromine and the chlorine. Bromine and the chlorine, they both are water soluble or they dissolve in organic solvent, either one, but the alkene is always dissolved in organic solvent. So when you want to mix those two together, especially if the bromine is dissolved in water, they're not going to be mixed. So this is why we need a solvent every single time to mix them together. To represent the di atom, the dihalogen, we represent it as a Br2 like this, or for simplicity, a Br single bond and another Br. For these types of reactions, the Br is going to add to the double bond, and whether the alkene is symmetrical or unsymmetrical, it doesn't matter, because I am adding a bromine and the bromine, so I'm adding two bromines that are the same, so they really doesn't matter where each bromine go, as long as you are adding them on the double bond. The idea is the same. You're adding around on the double bond, so you are breaking the pi bond of the double bond, and you are forming two sigma bonds in there. But because of the size of the bromine, whenever the double bond is locked in a cycle, locked in a cycle means you cannot get it out of the cycle. It is in the cycle. So if the double bond is locked in the cycle, you have to show the stereochemistry of the reaction. What does that mean? You have to show how the bromine is adding. And the bromine always, whenever you have a double bond that belongs to the cycle, the bromine is going to add a trans with respect to each other. So these two bromines, one bromine is going to add up, the other bromine is going to add down, or because both of these are considered to be somehow, okay, you can use any one of those, it's fine. You don't have to write them both. So I can have either the bromine added up or it can be added down, but the other bromine has to be opposite to it, and we call this a trans addition. And you can use only one to represent the product. So you don't have to write both of them. This is whenever the double bond is locked in the cycle. And again, notice that this is an addition reaction. An addition reaction happens on the double bond. So you are breaking the pi bond, and what you are forming here is two sigma bonds. This is what you're doing. So the idea is the same, but because of the size of the bromine that is too big, the other bromine has to attack from the other side. It cannot be, you cannot have both on the same side. The addition is always going to be trans with these halogen additions. Now, if you have a chain, if your double bond is in a chain, notice the difference. Here the double bond is locked in the cycle. So this is why we consider stereochemistry of the reaction. This is trans addition, and this is called the stereochemistry of the reaction. So if I ask you what's the stereochemistry of the reaction of the bromine addition to the alkene, this is a trans addition. This is the answer. It's a trans addition. Now, if the alkene belongs to a chain instead of a cycle, then in this case, the double bond is outside the cycle. So if the double bond is outside the cycle in there, my product is going to look like this, because I will be adding a bromine here and the bromine there, similar, right? But now I have what I can call a rotation around a carbon, single bond carbon. So I'm going to end up having a hydrogen, a bromine in here, and then a CH3. And then I'm going to end up getting, this is your cycle in there. So I can have a simple rotation around the sigma bond. I can have a rotation around the sigma bond in there. And if I do a rotation around the sigma bond, I can easily rotate. And I can end up having another structure which is exactly the same. This is a bromine over here. this is a CH, and this is a bromine, and then this is a CH3. Why I am doing this? I'm doing this to tell you over here that when the double bond is outside the cycle, the stereochemistry doesn't matter because I can do a rotation around the carbon, single bond carbon. I can twist that, I can rotate it because rotation around the sigma bond is possible. Rotation around the pi bond is not possible. Rotation around a cycle is not possible. So that cycle in here, the double bond is locked in the cycle. I cannot rotate the sigma bond after the pi bond is broken. So this is why the stereochemistry showing the trans addition is important. But here, if your double bond is outside the cycle, I don't need to show any trans addition. All I need to show is just the two bromines that are added. I can either show them like this or show them like this, and neither one of them are going to be trans in there. Because remember, to have a trans, you need to have it in a cycle or in a double bond. This is the rule for the trans in there, okay? And the trans and a double bond, you need to have double bond in there and substituents around the double bond. Same idea in here. Whether you're doing a symmetrical or unsymmetrical alkene, it doesn't matter. You do have your alkene in there, and your double bond is not locked in a cycle. So if it's not locked in a cycle, it does not matter the stereochemistry of the addition. All I want you to do is just add a bromine here, add a bromine there, break the pi bond, and show that you are forming two sigma bonds. So your product is simply gonna look like this. You have a bromine in there, and that is the sigma bond, and that's it. Please make sure to count the number of carbons that you are starting with. I am not adding any carbons. I have 5 carbons in here, and these are my 5 carbons in there. All I am doing is I broke the pi bond, and this is where the addition is. This is where the double bond was. So I added a bromine on one carbon and another bromine on the other carbon. Please don't show the stereochemistry of the bromine again, because you can have a rotation. You see them here as being opposite with respect to each other, but I can do a simple rotation and then make them on the same side. It really doesn't matter. So stereochemistry does not matter if you have the double bond in a chain, but it does matter if you have the double bond in a cycle. So if you're double bond in a cycle, then you need to show the stereochemistry of the addition. Just pick one, okay? You don't have to show both, but you need to show that one bromine attacks and is going to attack from the top. The other bromine is going to be at the back. Or you can show that, here you go, one bromine is at the back and the other one is going to be at the top. Just this is going to be your trans product. Just go ahead and pick one. You don't have to show both. Okay, that's the whole idea. Double bond locked in the cycle, you have to show your stereochemistry of the addition, and the stereochemistry of the addition is going to be a trans addition. We always said that whatever goes under the arrow, that is the solvent. So the solvent has nothing to do with the product. The solvent is just to make sure that the bromine and the alkene, those they do mix with respect to each other. Okay. The third reaction is the addition of hydrogen in there, and this reaction is very important, and it happens only whenever you have a metal catalyst. So without a metal catalyst, the reaction does not happen. So meaning, if you have an alkene and just the hydrogen in there, nothing above the arrow, then it will be no reaction. It will be no reaction in there. What makes the reaction happen is any of these metal catalysts. It's either PT, platinum, or it's nickel, or it's radon. Any metal of those, they allow the reaction to happen. And it's exactly the same thing, same idea. I am adding on the double bond. I am breaking the pi bond, and I will be adding 2 sigma bonds. So on each one of these carbons, I'm going to end up having a hydrogen. So my product in this case is going to be a hydrogen on this carbon, and a hydrogen on this carbon. As simple as that. And again, don't forget, you don't have to show it though. You don't have to show these two hydrogens because these two hydrogens were there. Remember, every carbon is 4 bonds. This is exactly the same. If I want to show it as a skeletal, then it's going to be my alkane. Specifically, it's going to be butane. So what I went from a butene. I went from 2-butene, and there's what I did. I went from 2-butene, it says carbon number 1, carbon number 2, so that is 2-butene in there, into a butane. This is what I did. I did not add any carbons whatsoever in there, and I did break the pi bond, and I made 2 new sigma bonds. This is a sigma, and this is a sigma. The reaction has a stereochemistry. Yes, it does. If I want to compare the size of the bromine to the size of the hydrogen, bromines are big. They are big molecules in there. So this is why when they add a trans with respect to each other. But hydrogen is a small atom. It's a very small atom. So hydrogens, when they add, when the double bond is locked in the cycle, hydrogens, they do add on the same side. So you have to show them on the same side. And the addition over here will show around these 2 carbons because this is where the double bond was. The double bond was here. So the addition is going to be here. So guys, you would need to show that the hydrogens are adding on the same side. Either both hydrogens are going to show to be up in there. So either 2 hydrogens are going to be up or the 2 hydrogens are going to be down. These 2 are the same, just pick one. So this is a hydrogen, this is a hydrogen. These 2 are the same. Just go ahead and pick one and show one. The product is going to be a cis product. So the stereochemistry of this reaction, it's going to be a cis addition. So the bromine addition is a trans addition. The hydrogen addition is a cis addition when the double bond is locked in the cycle. When the double bond is in the chain, we don't care. Just go ahead and add the hydrogens to the carbons of the double bond. See, here the double bond is outside the cycle. We don't care. So all what I want you to do is just highlight the double bond just to know that you are adding on these 2 carbons. You already have 2 hydrogens here. You're just going to add 1 hydrogen here and 1 hydrogen there. Neglect the stereochemistry because the double bond is outside the cycle. So I'm going to be ending or adding a hydrogen here and the hydrogen there. And then you have your 2 hydrogens there. Okay. And this is exactly the same as if I want to go ahead and show that as a regular skeletal structure. You don't have to show the hydrogens. So you go from an alkene to an alkane every single time. Now, remember that with these reactions, hydrogen is very reactive. When hydrogen reacts with a metal, these are very reactive. What does that mean? It means that the hydrogen will react with every single double bond in the structure. So this means that hydrogen will react with every double bond in the structure. Okay, so here, how many double bonds do I have? I have 1, I have 2, I have 3, and I have 4. The only double bond that is locked in the cycle is this one. So this one is the only one that I'm going to go ahead and show the stereochemistry for. And I'm going to show the stereochemistry. It's a cis addition. So I'm going to show both hydrogens either up or either down. They are the same. Okay, I'm just going to choose that to show them that they are up here. And then the rest of the molecule, I'm going to go ahead. I'm not adding any carbons. So the same number of carbons. My double bonds was between those 2 carbons in here. So I'm going to go ahead and add 2 hydrogens in there. I'm just going to show the skeletal. So adding 2 hydrogens here, you don't have to show them. but I'm moving from an alkene to an alkane, and then I am adding 2 hydrogens in there, and I am adding 2 hydrogens over here. Okay, so that is going to be my product. If you want to show the hydrogens, that's fine. You can show the hydrogens being added here. Okay, you have 2 hydrogens here and 2 hydrogens in there, but normally we like to keep it in the skeletal form and don't show the hydrogens. But these hydrogens you have to show because you have to show them being added cis with respect to each other. Another reaction in here for the alkene is the reaction of water in presence of an acid. The types of acid that we call this hydration. This means that you're adding water. The types of acid that we are using are sulfuric, phosphoric, and HCl, which is hydrochloric acid. The sulfuric acid, this is the lowest structure for the sulfuric acid. And the phosphoric acid is, this has a lowest structure of this over here. So you have an O, a hydrogen, and an O, and another hydrogen. So that is the lowest structure of the phosphoric acid. It's very important to know the lowest structure of the acid because this reaction is 2 steps. The first step, you always react your water with the acid and you do an acid-base reaction. This is a revision for acids and bases in the first part of the course, which is 111. So water will act as a base from its lone pairs. So the water is going to take the acidic hydrogen in there. This is an acid-base reaction. Base always takes the acidic hydrogen. So the base takes the acidic hydrogen and you're going to make the H3O+, which is the conjugate acid. So always whenever water reacts with any of these acids, the water is going to take the hydrogen from each one of those. So if you're working with H3PO4, it's this hydrogen that the water is going to take. If you're reacting water with HCl, it's this hydrogen that you are going to take to create the H3O+, which is the hydronium ion in there, plus the conjugate base. This is the first step of the reaction. So the hydronium ion is always forming in this case when water reacts with any type of acid. So how will the reaction be? Guys, this reaction has no stereochemistry. So the only 2 reactions that have stereochemistry are the halogen addition and the hydrogen addition. One is trans, the other one is cis. But the others, they don't have stereochemistry. This reaction is straightforward. And with this reaction, what we have here is simply the water. This is the first step. So always the first step, these 2 are going to react with each other. And when they react with each other, you are always going to make the hydronium ion, which is the H3O+. Okay? I normally like to write it like this because the H3O+ is going to add to the double bond over here. It's this one that is going to add to the double bond. How it's going to add to the double bond? It's going to add to the double bond by simply adding the hydrogen following the Markov-Nikov. Hydrogen will add to the less substituted carbon. So the hydrogen from the H3O+ will add to the less substituted carbon. This is the rule. And then water will add as an OH. So water here, it's going to add as an OH in there. So water is going to add an OH. So at the end, I will be ending up adding to the double bond a hydrogen and an OH. So it's as if I am adding water. So that's why I call this reaction hydration. And the OH adds to the most substituted carbon. So the OH adds to the most substituted carbon. Okay, this is it. So if I want to go ahead and write the product of the reaction, this is where the addition is going to be on these 2 carbons. So locate which one is the most substituted, which one is the least substituted. This carbon is the least substituted or the less substituted, and the top one is the most substituted. So now I know where the hydrogen is going to add and where the OH is going to add. So the hydrogen is going to add to the less substituted carbon. So the hydrogen simply, it's going to add here. Let's put it in a different color. Here you go. So this is going to be the hydrogen in there. This is the new sigma bond that I made. You already have a hydrogen here. You can simply keep it over there. And then I do have a CH3 in here. I'm going to keep it, but I am adding to the most substituted carbon NOH in there. And this is the other sigma bond. So I ended up adding water. This is why I call this a hydration reaction. There will be no stereochemistry for this reaction. Okay, whether the double bond is in a cycle or the double bond is in a chain, it really doesn't matter. Just highlight these two are going to form H3O plus, and H3O plus will add hydrogen to the less substituted and will add the OH to the most substituted. It's enough to know which carbon is the least substituted. This one is the least substituted. So hydrogen adds here, and this carbon over there is the most substituted. So OH adds here. Okay, and then go ahead and draw your product in there. So here you go. This is your product. You are adding your OH on this carbon. You can draw it anywhere you want. I can draw it here, for example. I can take that and draw it over here. Remember, this is a tetrahedral carbon, so it really doesn't matter where you draw it. And then on this carbon, I do have my hydrogen in there, and this is going to be your addition. The last reaction for alkenes is the polymerization. And polymerization is a process of making a polymer. So how you make a polymer? You make a polymer by simply using the small repeating units, which we call monomers. So you react those monomers together. And the way that you react those monomers together, you have n number of molecules, meaning a lot of monomers in there. That's why we say it's an n number of monomers in there. And those monomers, they start reacting with each other from the reactive site, which is the alkene. So the double bond of the alkene opens up and make a new bond between this carbon and this carbon, and so forth. This double bond opens up and make a new bond between this carbon over here and this carbon over there, and so forth, so that you can make a chain in there. And that chain is called a polymer chain. The polymer chain will be made up of repeating units of the monomer. So the monomer here is made up of two carbons. So you're going to have two carbons, two carbons, two carbons, and in between there is the new sigma bond that you formed. This is an example of a polymer which is made up of three monomers in there, three monomers that are the same. So this is how we write it. And of course, the bigger the polymer in there, you need an abbreviated way in order to express or write that polymer. So in order to represent a polymer, we represent it by its monomer repeating unit. Okay, so what we do over here is that we see what is the monomer, and the monomer here is simply two carbons. So we take out the double bond of the monomer, and what we do is we just draw two lines in there. We draw the brackets and we put N, and this is the repeating unit of the polymer. So this is the same as that. This means that the repeating unit is repeated n times, depending on how many n times that is. The rule says that whenever you are working with polymers, you have to know the monomer unit. And the monomer unit should always be an alkene, because it's that alkene, it's from the double bond that is going to open up to make a new sigma bonds. So when you are representing your alkene, when you are representing your polymer, what you do is you choose what is your repeating unit. My repeating unit is 2 carbons here, so I just draw the 2 carbons without drawing the alkene, and then I draw 2 lines because those alkenes are going to be bonded to each other, and then start my brackets in there, and then to the end. And that is going to be the polymer repeating unit. So this is called the polymer representation. Polymer representation. Okay, so that's the polymer representation of the repeating unit. Okay, so what I have here is my polymer. To name that polymer, I always look at the name of the monomer, and simply I add poly to it. So the IUPAC is ethene, so the polymer name is polyethene, or I can go with the common and it's going to be polyethylene. Same idea for the second example in there. I'm starting with a vinyl chloride. You don't have to know the name. I will give you the name of this alkene. Okay, if I want to do polymerization and I ask you, go ahead and draw the representation of the repeating unit, it's really easy. I am starting with N molecules of this monomer. So this is a monomer. And I am reacting those monomers with each other, N of them, in order to form a long polymer chain. So in order to draw that polymer chain, you take that monomer exactly as is. So I have a CH2 without the double bond though, and the bond and the CH in there, and the chlorine. So this is my alkene part. I don't care about the chlorine. It's the alkene part in there. So it's the alkene part that is going to be repeated together with whatever substituent you have on it. You just go ahead and put it in there. And then you are going to open up the chain in there, or you're going to put your brackets in there, and then you're going to put N, and this is the representation of the polymer. The polymer will be named poly, and then the same name as the monomer, which is vinyl chloride. Okay, it's polyvinyl chloride because you do have a vinyl and the chloride. You have two options: either leaving it without the brackets, or you can put poly and then open the brackets and do vinyl chloride in there, because the vinyl is different than the chlorine, and this is why. So either one of those is acceptable for the name of the polymer, and that is the polymer representation of the repeating unit. Let's have another example here, and that other example is butene. So if I want to draw the polymer for butene, the polymer representation, same thing. All I care about is that double bond in there. Okay, I know that I have on the butene, I have the ethyl group. So in order now to draw that, I'm gonna go ahead and draw my my 2 carbons. So these are my 2 carbons. I'm gonna go ahead and draw them, and then draw 2 lines in here and open the brackets. This is the N. And if you want to number this on the second carbon, I do have my ethyl group. So I'm just going to go ahead and place my ethyl group in here. And that is going to be my repeating unit in there. So the repeating unit is basically the double bond, because the double bond is the reactive part of the molecule in there. And then whatever is connected to the double bond, you just go ahead and put it as a substituent. Same thing in here. N molecules of this compound in there. You don't have to know the name. So again, I care about this double bond. It's made up of 2 carbons. So I'm just going to go ahead and put those 2 carbons over here. Put 2 bonds in there. Open the brackets. Open my brackets, and whatever is on this carbon, on the second carbon, I do have a carbonyl, And I do have a CH2 and a CH3. So that is a CH2 and the CH3 in there. So I just go ahead and put them, and that is going to be to the end. And that is going to be my repeating unit, my polymer representation of the repeating unit. It's exactly the same as this, it's exactly the same as putting all of these structures next to each other, and then you are reacting them next to each other in there, so that you are forming a bond between this carbon and this carbon, and then you're forming a bond between this carbon and this carbon, and then this carbon and another carbons, and so forth. So the only part that is being reacting with each other is actually the alkene. You're forming bonds between the carbons of the alkenes in there, and the substituent on the alkene stays the same. So this is why when you want to represent that polymer, you want to make sure that the repeating unit is your alkene, and then any substituent on the alkene, make sure that you go ahead and you place it in there.